Hey Science fam, today we're going to learn about what we call the VSEPR Theory, which is an acronym for, if you really break it down, it's pretty simple. Valence shell electron. Valence, remember, is the outermost electrons, all right? And we know that electrons are found in pairs and that electrons repel themselves. So valence shell electron pair repulsion just talks about how electrons want to be as far apart as possible. And because of that, when we make different compounds, when they're formed, they're going to try to spread out as much as possible. And because of that, they start to make similar shapes depending on the compound. First of all, why would anyone even care about the shape of a compound? Well, depending on the shape, actually determines its function, right? So think about something as simple as like hemoglobin, which I guess isn't very simple, but the idea that it's important. We need hemoglobin in order for oxygen to bind to the iron on hemoglobin, and it has to be the right shape to do that. And once that oxygen binds to the hemoglobin, if you remember from biology, then that goes around our body, and that's how we can move our oxygen throughout and survive. So depending on the shape, also determines the molecule's function. It also can determine the taste of the molecule, right? Is it sweet, salty, sour? And also if it's dangerous or safe. Can it bind to different proteins in your body, which can screw up function, which could eventually be dangerous, right? So shape in the chemical world is actually really important for a lot of how it affects us. So when we look at the VSEPR theory, now that we've tackled Lewis dot diagrams and we see all the different outside valence electrons and how they affect bonding, we can start looking at, all right, if these electrons that are around an atom are trying to repel and spread out as far away from other electrons from other atoms in the molecule, that pushing and pulling can actually create a certain shape of the molecule. And what does the molecule do? It spreads out as far as it can so that it has the lowest energy possible. So just like why electrons are shared in covalent bonds or they're transferred in ionic bonds, everything is about being more stable and having lower energy. So in the VSEPR theory, it helps us understand why molecules spread out a certain way, and it has to do with just finding the lowest energy possible. We're going to learn a few shapes in class. There are more than the shapes that we'll learn, but these are the basic ones, all right? So first of all, shape number one is the most simple. It's a linear shape. So if each of these are an atom, all right, and it could be more than two, there could be 3 atoms, this could be a double, single, or triple bond, but when it's straight across like that, we call that shape linear. So when we do our ball and stick models, when we use our molecular model kits, and any of them that are straight across, regardless of their single, double, or triple bond, and they basically have an 180-degree angle between the two atoms, that is considered a linear shape, right? An example, simple one, all the diatomic molecules, which we call Brinkelhoff for short, that's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Those 7 molecules naturally occur in pairs with themselves. So bromine is never found all alone by itself as just Br. It actually would be Br2. Iodine would never be alone, it would be I2. Nitrogen binds with itself to make N2. Chlorine, hydrogen, oxygen, and fluorine. Whenever they're found alone in nature, they're actually found paired up with themselves. Because of that, we call them diatomic, meaning they don't like to be alone. But those 7 right there, the way to remember them, it's a silly word, but it's easy to remember, is Brinkelhoff. And if you look on the periodic table, Brinkelhoff actually makes the shape of a 7 on the periodic table, besides the 1 hydrogen. But we'll look into that further in class as well. But again, all those diatomic molecules, they're all linear because there's only 2 of them. Carbon dioxide is another example of that. The double bonded oxygens, that's a straight across linear molecule. And you may have seen that when making that in your molecular model kit. The next shape that can be is bent. And you might think, well, why would anything, if it's trying to repel as much as it can, why wouldn't it be straight across? Wouldn't that be the farthest away as possible? But remember, sometimes we have lone pairs of electrons. And remember, those lone pairs of electrons are still there and repel as well. So they push down that linear molecule to a bent shape. All right? Again, remember VSEPR is valence shell electron pair repulsion. So the fact that these lone pairs are repelling as well pushes down some of these atoms so that it gets that bent shape. All right, so if we look at the angle of a bent shape, most bent shape molecules have a 105-degree angle. And an example, a common one, is water, H2O, right? Because of that shape, we know that oxygen gets more negative and hydrogen gets more positive. And because of that, that can lead to hydrogen bonding in that. So remember, the shape does affect its function. The next shape we're going to learn about is called trigonal pyramidal. Say that to yourself, trigonal pyramidal. It's like a little mini pyramid. So there's a head and then there's 3 legs coming off of it, all right? The angle between those legs is 107 degrees, all right? Now, NH3 is a great example of that because the nitrogen sits on top and the hydrogens form little legs. And again, if you're thinking about repulsion, repelling each other, you might think, why isn't it flat like a pancake? But remember, there's an extra lone pair of electrons on that nitrogen that aren't part of bonding. So those lone pairs of electrons actually spread out more and they push down those hydrogen legs. So that's why you can actually end up with a little pyramid instead of just a flat 3-sided molecule that's flat like a pancake. So that's called trigonal pyramidal. This one is flat like a pancake. It's called trigonal planar. Say that to yourself, trigonal planar. Now this one is flat like a pancake. So just like it's drawn here, you can see that it has the center molecule and then 3 legs going off. If you divide a perfect circle into 3 parts, obviously 360 degrees divided by 3 is 120 degrees. So it makes sense that bond angle is 120 degrees. An example of that is like this, where we have carbon, a single bonded hydrogen, and a double bonded oxygen. It is flat like a pancake. It's not like a pyramid, so therefore we call that trigonal planar. The last shape we're going to learn about, though, remember there are more shapes than just all 5 of these. There's trigonal bipyramidal and a bunch of other ones. But for this one, tetrahedral, it's like having a center element with 4 legs perfectly spread out. Now some people might say, well, why would it look like that? Wouldn't it be more like a cross where they could spread out even more? But remember, in the 3 dimensions, right, these guys might repel each other more by being that close. So that's why you end up with this 3-dimensional shape called a tetrahedral. Now remember, tetra stands for 4. 1, 2, 3, 4. So tetrahedral has 4 legs. The bond angle between the 2 atoms sounds like a radio station, 109.5 degrees, right? And methane is probably the most common one. To give an example of tetrahedral, it has 4 legs coming off of it with the carbon in the center. All right, and it sits up like a little tripod that has a head on top of it. That shape's called tetrahedral. Say that to yourself so you know how to say it, tetrahedral. Since we've been talking about shape and function, there is one more thing that overlaps dramatically with shape and function, and that's polarity. Polar molecules, if you remember when we talked about intermolecular forces, IMFs, remember, polar molecules come from what are called dipoles. Dipoles are when there's uneven sharing of electrons. For example, between this oxygen and hydrogen. Oxygen is so much more electronegative. So you find electrons around oxygen more often than hydrogen. So that means overall that oxygen tends to be more negative on that side and hydrogen tends to be more positive. Because of that, you can have interactions between other sides and other molecules and atoms because they have partial negative and positive charges. Remember, that positive and negative side of a molecule is called a dipole. So if we look at covalent bonds, even though they're sharing electrons, they aren't always sharing them equally. So if you have unequal sharing of electrons, all right, we are going to call that a polar covalent bond. polar meaning that there's an unequal sharing. Again, like in water, which we talked about with hydrogen bonding. Because oxygen pulls way more on electrons than the hydrogens, this is considered polar covalent bonds because the negative side is by oxygen and the positive side is by hydrogens. So because of that, we call those polar covalent bonds. Now, if it's an equal sharing where they're not unevenly pulling on electrons, then we would call that a nonpolar covalent. And to the opposite extreme, if there's so much pulling that it's a totally ridiculous unequal amount of sharing where it's basically just a positive and negative charge coming together, that's when we get ionic bonds. So ionic bond is the true ultimate polar bond. But don't forget, a lot of covalent bonds are polar, meaning that one atom's pulling on electrons more than the other, which means it's more negative. Okay, so if we look at the bonds between different elements and we look at their electronegativities, which by the way, electronegativities are given on a chart, they're given a number. So for example, this hydrogen and chlorine bond, hydrogen has an electronegativity of 2.1 and chlorine has an electronegativity of 3.0. We would have to look that up. You wouldn't memorize that. But because chlorine has a larger electronegativity, that makes chlorine's side more negative and hydrogen side more positive. The way we say that with like a little negative or a little positive are these little symbols right here. If you do that with a negative or positive, it means partially positive or partially negative, just so you know. All right, so if we look at this element right here, you can see that there's unequal sharing all over the place with electrons. Hydrogens have low electronegativity 2.1, carbon has 2.5, and oxygen has 3.5 electronegativity. So oxygen is really pulling on those electrons that have more negative charges around them. So because of that, we know that there's way more negative charge around oxygen than carbon. Because of that, we're going to have more of a polar covalent bond. So just to wrap up the idea of shape and function and polarity, if you have two elements that have different electronegativities, the side that's more electronegative means that it's pulling more on the electrons. So chlorine will be more negative charge, hydrogen will be more positive. That's a polar covalent bond. But if you have nonpolar molecules, that means that there's even sharing. Just like the diatomic molecule chlorine. It has chlorine and chlorine. They obviously have the same electronegativity, so they're pulling on each other equally. So that means it's nonpolar because there's no dipole. There's no positive and negative end. All right, Science Fam, hopefully this has helped in getting you interested and more in tune with molecular shape and molecular function and also molecular charges, meaning polar and nonpolar. Thanks for listening. Good luck.